Hello, friends. Welcome to the online lecture series of Basics of Computer Network. Myself, Assistant Professor Mr. V.R. Vadekar from Department of Electronics and Telecommunication from Matoshi College of Engineering and Research Center, Nasik. As we know, we are studying unit number 2, that is error detection, correction, and data link control. So let's start with our today's lecture. So before starting our today's lecture, let's have a quick revision. So if you remember, in our previous lecture, we came to know about error detection. What is error detection? How it can take place? What are the types of errors? That is a single bit errors or burst error. What are block coding and why is it so important? Today, we are going to study about a linear block codes. So basically, linear block code, it is a subset of block coding. Now the question is, why we call it as a linear block codes? A linear block code, it is a code in which the exclusive or the addition, that is a modulo 2 addition of two valid code words, it is going to create another valid code words. There are also a non-linear code words also, but their structure is and the implementation is very difficult. So we are going to concentrate on linear block codes. As I already told, in a linear block code, the exclusive or the XOR of any two valid code words, it is going to create another valid code words. So let us see if the two codes that we are going to define in table 1.1 and 1.2, they belong to the class of linear block codes or not. Now the scheme in table 1.1, it is a linear block code because the result of XORing any code word with any other code word, it is what? Valid code word. For example, the XORing of the second and the third code word, it is going to create the fourth one. So let's understand by this using this table. Now suppose if we are going to XOR these two code words. So 1, 1, it means two similar bits are there. So what is the resultant? It is 0, since there is a no change. Similarly, if you are comparing 1 and 0, so it is dissimilar codes. So the output of XOR, it is what? 1. And last, 0, 1, since two bits are different, so the output, it is what? 1. So you can observe it that this is the valid code word present in this table. Similarly, if you are going to make a XOR of these two code words, suppose now you are going to make it 1, 0. 1 XOR with 0, it is what? 1. Similarly, this one, it is XOR with, that is a second code word, and this is a fourth code word. So 1 and 1, it is what? Similar bits. So output of XOR gate, it is what? 0. And last, 0 and 1 over here. Since two dissimilar bits are there, so the resultant is what? 1. It means 1, 0, 1. So we are getting what? A valid code words. So that's why it is called linear block code. Now, similarly, the scheme in table 1.2, it is also a linear block code. So we can create all four code words by XORing two other code words. So now let's understand by using a table this. So suppose you are going to make a XOR of these two pattern, that is a code word, second code word, and this is your third code word. So XORing of second and third code word, it would give you one, this fourth code word. So let's see this. Now, since it is a 1, 1, so the output is what? 0, because two similar bits are there. 1, 0, two dissimilar bits are there, so output it is 1. Similarly, 0, 1, two dissimilar bits, the output again it is 1. XOR of 1 and 0, it is 1, and the XOR of 0, 1, it is also 1. It means it gives rise to a new valid code word. Now again, you can verify this by XORing this second code word with this fourth code word. You would get the valid third code word. Now see, 1, 0, XOR of 1, 0, it is what? This 1. Now similarly, XOR of 1 and 1, it is 0. Similarly, XOR of 0 and 1, it would give you 1 because two dissimilar bits are there. Then XOR of 1 and 1, it is 0. And similarly, XOR of 0 and 1, it gave you 1. It means what we have concluded, that exclusive or XORing of any two code words, it is going to generate a new valid code word. Now, in our first table, 1.1, the number of ones in the non-zero code words are 2. So the minimum distance is what? 2. And similarly, in table 1.2, the number of ones in the non-zero code words are 3, 3 and 4. So out of which 3 it is the minimum. So in this code, we are having minimum having distance, it is of 3. Now, perhaps the most familiar error detecting code, it is what? A parity check code. This code, it is a linear block code. So in this code, basically, k-bit data word, see this k-bit data word, it is changed into an n-bit code word, whereas n is equal to k plus 1. So this extra bit called the parity bit is selected to make the total number of ones in the code word even. Whereas, some implementations are also there which specify an odd number of ones. So we are basically concentrating of even number of ones. So the minimum Hamming distance for this category is d minimum is equal to 2, which means that code is a single bit error detecting code. Getting, guys? Now you can see this table. It is also a parity check code with k is equal to 4 and n is equal to 5. So you can see this is the data word and it is a one-to-one corresponding code words for it. So instead of sending this data word, we are going to send this code word. And please note down this table, guys, because for further lectures, I am going to, we are going to refer this table. So please note it down. And you can see if a data word 1010 it is there, then we are going to transmit the code word 10100. Similarly, if the data word it is a 1001, we are going to transmit it 10010. So it is so on. In further lecture, we would see how we are going to calculate this code word. But right now, we are going to focus on the encoder and the decoder for this simple even parity check code. So this is the sender who is going to create a code word. This is a data word. Just wait a minute. So this is the data word A0, A1, A2 and A3 from which we are going to generate over here. If you will see the data word, it is of 4 bits, A0, A1, A2, A3. A0 is LSB and A3 is MSB. And from this data word, we are going to create a code word which is of 5 bit. So what we are going to do it, we are going to add this extra bit which is called as parity bit denoted by R0. And this R0, it is generated by this generator. So you can see at the input of the generator, there are 4 inputs, 4-bit inputs. That is the data word it has been given to it. And depending on the calculation, it is going to generate a single bit. Now we will see this encoder in detail. And when this code word, it is transmitted, it is received by this receiver. Then you can observe it, this code word, which is of 5 bits, it is given to this checker. So the input to this checker, it is a 5 bit and output it is of 1 bit. And the output of checker is denoted by S0, that is nothing but your syndrome. And depending on the value of this syndrome, the decision logic, it is going to decide whether you need to extract the data word from this code word or you need to discard this one. So let's see in details now. First, we would focus on this encoder. Now this calculation is done in modulo arithmetic, guys. The encoder, as I already told, it uses a generator that takes a copy of a 4-bit data word, that is A0, A1, A2 and A3. And it is going to generate a parity bit, that is R0. And this data bits and the parity bit together, it is going to create the 5-bit code word. And remember, the parity bit that is added, it makes the number of ones in the code word even, because we are going to see the example of what? Even parity. So this is normally done, by adding the 4-bit data word, that is, we are going to perform a modulo 2 arithmetic, that is A0 plus A1 plus A2 plus A3, modulo 2 arithmetic, and the resultant is denoted by R0. Now, if the number of ones is even in this one, if the number of ones is even, then R0 is equal to 0. If the number of ones is odd, then the result is 1 over here. So in both the cases, the total number of ones in the code word is what? Even. Then this sender, it is going to send this code word to the decoder. Now, the code word may be corrupted. This code word, which is received by the receiver and sent by the sender, it may get corrupted, during the transmission. And the receiver, it is going to receive this 5-bit code word. Now you can see the position of the checker at the receiver. It does the same thing as the generator in the sender, with one exception, that is, the addition is done overall 5 bits, whereas generator, it was doing the overall addition of 4 bits. And the result of this checker is called syndrome, denoted by S0. And remember, the syndrome is 0 when the number of ones in the received code word is what? Even. Otherwise, its value is 1. So you can see syndrome, it is just a 1 bit, and syndrome is 0 when the number of ones in the received code word is even, otherwise it is what? 1. Now, this is the modulo 2 addition of this received code word. Over here, R0 is replaced by Q0, A0 is replaced by B0, A1 by B1, A2 replaced by B2, and A3 replaced by B3 at the receiver side. Then this syndrome, is passed to the decision logic analyzer over here. As I told, if the syndrome is 0, there is no detectable error in the received code because the number of ones in the code word is even. And then the data portion of this received code word is accepted as the data word. But if the syndrome value is 1, then the data portion of the received code word is discarded. So the data word is not created. So this is the encoder and the decoder that we understood. Now let us look at some transmission scenarios that assume the sender, it is going to send the data word 1011. So please note down this example, guys. And the code word which is created from this data word, it is 10111. See, you can observe it over here. The syndrome value is, 1. Why is it so? Because in the data word, the number of 1, it is odd. In order to make it even, the generator, it is going to add a parity 1. So the total number of ones in this created data word is even, and which is sent to the receiver. So let's examine the 5 cases. First is, no error, it occurs if the received code word is 10111, because the syndrome is what? 0. So from which this parity is discarded, and we are going to extract this data word from this code word, that is 1011 is created. Second scenario. Now, one single bit error, it changes A1. So first I would tell you, since this is 1011 and this is a parity, so parity, it is denoted by, say, R0. This is your A0, this is A1, this is A2, and this is your A3. So don't get confused. So one single bit error, it changes A1. Then the received code word, what it is? It means this one. This has been changed, 1 to 0. So the received code word is 10011 instead of 10111. So the syndrome is 1 over here because the number of ones in the code word is what? Odd. Since it is odd, the syndrome is what? 1. So no data word is created, it is discarded. Now the third scenario. So one single bit error, it changes R0. It may happen that parity bit, it may change. So if it is 1, now the syndrome, see, the parity bit, it gets 1, it gets corrupted. So number of ones in the code word is odd. So the syndrome is 1, hence no data word is created. Now the fourth scenario, an error changes R0 and a second error, it is going to change, that is A3. Hence, the received code word, it is 00110. So you can find the number of ones in this code word is even, and the syndrome, so syndrome it is what? 0. So what is the data word? The data would be created, it would be what? 0011. So, and note that here the data word, it is wrongly created because what? Due to the syndrome value. What it shows? It shows that simple parity check decoder, it can't detect an even number of errors. Although error it is occurred, but it is not detected. So this is a problem with this parity check. So now these 3 bits, suppose A1, A2, A3 are changed by errors. Then the receive code word, it would be 01011. So again, the number of 1, it is odd. So the syndrome is 1. Since syndrome it is 1, the data word is not created. Which shows by, comparing these 5 scenarios, the simple parity check, it is guaranteed to detect one single error and can also find any odd number of errors. But it couldn't detect an even number of errors. So as we have studied the even number, a parity check, it can also detect odd number of errors. So students, today we have studied about linear block code. That is simple parity check code. It is a subset of your linear block codes. Why we call it as a linear block code. Then we have studied the encoder and the decoder of this one, and how we are going to tell whether the code word it is transmitted correctly or not from the syndrome value. That is, if the number of ones in the code word it is even, then we can say no error it is introduced. Otherwise, error it is introduced in that one. This is the assignment that you need to solve. So please note down this assignment. In next module, guys, we are going to see the another block code, that is cyclic code. Here it is my email address on screen. So thank you very much, students, for today's lecture.